Alright, so good morning. I posted 2 tutorial videos on Canvas about integration by parts and how to solve first order differential equation using separable method. Alright, so the first clip was a calculus, the knowledge from a calculus class, and the second clip was from Math 3133. Basically, so I posted chapter 1 of Haberman online, and also I posted this video to help you review a separable method. Alright? So you can watch those tutorial videos to review, for instance, first order differential equation. I also posted 2 practice exams. So the first one was, so in this exam you're going to have only one problem, which is 20 points. And also another optional problem, which is also another 20 points. The practice exam 3 and the practice exam 4 will contain basically the first problem, which is the one that you have, and then the second one, which is optional. So basically practice 4 will be for the optional questions. But I'm gonna do practice exam 4 in class because so what you observed from the previous exam, that the optional questions is related to the next lecture, right? So normally in the previous questions I put the optional questions, but the optional question is the material for the next lecture. So basically when I do when you do the optional questions, you will understand the material after the next class, right? So in this case, I put the heat equation in the optional problem, so that you understand that okay, this is what we are going to learn, and this is the PD problem, right? Questions? Skip. Now let us try to solve the. So in the previous class, we have this equation. X squared u second plus x u prime plus lambda u to be 0. All right. We solve this on 1 is smaller than x, smaller than a, and with the boundary condition u1 to be 0 and ua is also 0. From the previous class, this is what we've learned. 1, if you consider this operator fu is x squared u second plus x u prime. All right, so the operator is the one that involves u and not the lambda. In this case, the operator is x squared u second plus x u prime, right? This is the operator. Now, when you talk about operator, you need the boundary condition, right? For this one, we know that this operator is not self-adjoint. So L, U is not self-adjoint with the standard inner product. So from the previous class, we know that this operator is not self-adjoint under the standard inner product. This is why you have to find a new inner product. Which is FGW is equal to integral from 1 to a Wx Fx Gx dx. So this W is the weight, right? this operator is not self-adjoint. The key idea now is to define a new inner product so that this operator is self-adjoint with this weight. And the weight that we found is Wx will be we found what? We found 1 over x, right? Negative 1 over x? Or 1 over x? This is, I think 1 over x, right? And?
I think it was.
So yes, so you want. So how do you find this? You want to write u to be w x squared 1 over you divide both sides by w, right? X squared u second plus w x u second. All right, and you make this derivative to be this guy. So you have wx squared prime to be wx. Right? So this is what we have. I don't remember what it's w. So the key idea of finding w is that you multiply, you divide everything by w, and then here you have you multiply w with x squared, and you have to take the derivative of wx squared, and it's going to be wx, right? So I think 1 over x is good, right? Because when you replace 1 over x, then you have wx squared will be 1 over x times x squared, and this is x. So wx squared prime will be x prime, and this is 1. So w times x is 1 over x times x, and this is 1. Now, so I explain again. For this kind of problem, you have this equation with Differential boundary condition, right? So this is the operator with the same boundary condition. This operator is not self-adjoint. So you have to define a new inner product so that this operator is self-adjoint. What we do is to find the weight w, and you multiply w to the inner product. The simple process is that you divide, you write L under this term, you divide by w and you multiply by w. So here you have wx squared and here you have wx, and you have to set wx squared prime to be equal to wx. Yes?
For the second one, term, should it be u prime or u double?
Thank you. Excellent. Thank you. Yes. This is the 1 prime. Can you sign at the back of the paper, please? Thank you. What you need to do is to set the coefficient of w second to be the antiderivative of the coefficient of the w prime, right? In the previous example, we know that w is 1 over x because when you multiply 1 over x to x squared, you get x, and you take the derivative, you get 1. So w times x will be 1. This is the whole process, and this idea is the key. This is the key idea. All right. Now, what we are going to do today is to try to solve this eigenvalue problem, right? So solve the eigenvalue problem. The eigenvalue problem. Right? Now you have to solve this eigenvalue problem. So this has a much different form. This has a very different form from the previous example, right? So you have x squared, you have x u prime plus lambda u is 0. this is, then you have a method from the previous class. Sorry for that, because we have to go back a lot of times to the previous class, but the method is what? The characteristic equation is the method that works only for constant coefficient equation.
I see.
Right, so now I'm gonna recall. If you have like x second plus u prime plus u is equal to 0. For instance, you consider the characteristic equation. You have r squared plus r plus 1 is equal to 0, right? So this method is a constant coefficient equation. Constant coefficient. For this one, equation doesn't have constant coefficients, so you have to use a different method. Again, this is guessing, but so we guess that ux is x to the power r, and you plug this back to the equation. This is the key, right? So we guess that the solution has a polynomial form, which is x to the r. I is a constant that we have to solve later. And we plug this back to the equation, right? So you're going to have ux is x to the r, which means that u prime of x will be x r minus 1. And u second of x will be as r minus 1, x r minus 2. Right? For this, you guess that the solution has the form polynomial. So to remember this trick, you can keep in mind that, okay, for this case, the solution will be ux will be exponential rx, right? I is the solution of this one, right? So when you solve this one, you have the first and you find so in this case you have 1 square minus 4 is negative, so you found r to be minus 1 plus square root 3 over 2, 1, 2, right? So ux. So let me change a little bit. So this I'm gonna put 3 here, so that is constant. So you're gonna have r1 to be minus 3 plus 3 square minus 4 is 5 over 2, right? So ux will be e to r1x c1 plus c2 e to r2x. So for the constant coefficient case, you work with the exponential. For this case, you work with the polynomial, right? So that for this class, let us restrict to these two cases, right? The first case is the constant coefficient case. So they're all constant, right? So here this is constant, and this is also constant. So this is constant coefficient case. In the constant coefficient case, we stick with exponential. So we go back to the characteristic equation, and then you get exponential. For this case, you don't have constant coefficient, and we guess that this is polynomial. So now I'm gonna have ux is x to the r, u prime of x is r minus 1, u second will be this one, right? And I'm gonna plug everything back to this equation. I'm gonna have x squared u second plus x u prime plus lambda u will be x squared r minus 1, x r minus 1, 2 plus x r minus 1 plus lambda xi. All right? And this gives you what? This gives you x squared r minus 1 plus r plus lambda. This is x squared r squared minus r plus r plus lambda. So this is r squared plus lambda. Right? So in some sense, you still have a characteristic equation. Right? So you're gonna set 0 to be u x squared u second plus x u prime plus lambda u, and this is x no, this is xr r squared plus lambda, which means that r squared plus lambda is 0. So in some sense, you still have a characteristic equation. So let me explain again this point. The difference between this case and the case when you have constant coefficient is that for the previous case, you work with exponential. For this case, you work with polynomial. All right. So in our class, if the equation has constant coefficient, then you work with exponential. And if you don't have constant coefficient, you work with polynomial. All right? Now, you plug this polynomial into the equation, and you find another characteristic equation. So you have ux is x to the power r, u prime will be r x r minus 1, u second is r minus 1, x r minus 2, right? So now you have x squared u second plus x u prime plus lambda u, which is this equation. You're gonna get x squared r minus 1, x r minus 2, because here you replace this formula into this equation, right? You just plug the polynomial into the equation. You have u second is r minus 1, x r minus 2, so here you have x squared. You plug u prime to the equation, and you get rx r minus 1, right? And the leftover is lambda u is lambda x to the r. You group everything. You have, now you observe that when you multiply x squared with x r minus 2, you're gonna get x to the r, right? And when you multiply x with x r minus 1, you also get x to the r, right? When you multiply this guy with this guy, you get x to the r. When you multiply x with x r minus 1, you also have x to the r. The level is x to the r. So I put this as the common factor, right? And I get r minus 1 plus r plus lambda. I expand r minus 1 to be r squared minus r, right? And here I have r, and here I have lambda. At the end of the day, I have r squared plus lambda. And when I set this to be 0, because the solution of the equation has to be 0, right? So you want to solve this equation, and then this is equivalent with 0 is x to the r squared plus lambda, which means that r squared plus lambda is also 0, right? So to summarize, only in this class, because they are the equation. So summaries, constant coefficient, you have what? You have e to the r, and then you have characteristic equation. Non-constant coefficient. you have x to the r, and you have characteristic equation as well. All right? It's clear? So, explain again. For the constant coefficient case, the solution is of the type e to the r, where r is the solution of the characteristic equation, right? So, for instance, this equation, you have 1u secant plus 3u prime plus 1u is 0. The characteristic equation will be r squared plus 3r plus 1, right? Now, you're gonna find two solutions, minus 3 plus or minus square root of 5 over 2. Then the solution will be the linear combination of exponential of r1x plus c2 exponential of r2x. In this case, this is the same, except that you have a polynomial. So you have this polynomial, and r is the solution of this guy. X squared plus lambda is 0. Questions? And how do you find this characteristic equation? This is more complicated than the previous one, because in order to find this equation, you have to plug this form back into the equation, and then at the end of the day, you found this this characteristic equation, right? Question? It's clear? Right. So now let us try to deal with this characteristic equation. So you have characteristic equation. You have r squared plus lambda is equal to 0. This is the characteristic equation. So what should we do?
Move lambda to the other side and then go to the cases.
Right. You have to do 3 cases. Can you sign the back of the paper, please? 3 cases. Case number 1. All right. So minus lambda is positive. Lambda is negative. Right. When lambda is negative, you have r squared is minus lambda, which is positive. So you're going to have r1 will be square root of lambda, and r2 will be minus square root of lambda. So you're going to do the same. Because the characteristic equation in this case is r squared plus lambda 0, you consider 3 cases like in the previous case. But the only difference is that you replace exponential by x to the r, right? So you replace this by this, right? So then you're gonna have ux will be c1 x to the r1 plus c2 x to the r2, right? For the remark that for the constant coefficient case, ux will be c1 e to the r1 x plus c2 e to r2x, right? So you need to replace only the exponential by x to the power, right? So you replace the polynomial, the exponential by the polynomial only, right? You can follow these questions. It's clear? Right, so now let us continue. So ux will be c1 x to the square root of lambda plus c2 x to the square root of minus square root of lambda. Right? Right, so now you're going to replace r1 to be square root of lambda and r2 by minus square root of lambda. And you get this one. The next step is one. Boundary condition, right? Can you sign the back of the paper, please? So you have boundary condition. Boundary condition 1. You have what? You have u1 is 0, which means that 0 is C1 times 1 to the square root of lambda plus C2 1 to the minus square root of lambda. Right? So this means that C1 plus C2 is 0. So C2 is minus C1. Right. Replace into U. So you have Ux will be C1 x to the square root of lambda minus C1 x to the square root minus lambda. Right. So the whole process is the same, except that you replace exponential by the polynomial. In this case, you have the characteristic equation has two solutions. Square root of the absolute value of lambda and minus square root of the absolute value of lambda. So Ux will be the linear combination of this and that. The first boundary condition, U1 is 0. Then you have 0 is C1 times 1 plus C2, 1 minus square root of lambda. So this is going to be 1 and this is going to be 1. So 0 is C1 plus C2. So C2 is then minus C1. You replace this into U. So Ux will be C1 x to square root of lambda minus C1 x to square root minus lambda. Questions? The next step is case 2, right? So the next step is going to be this boundary condition. Case 2, boundary condition number 2. So let me do it. Boundary condition number 2, you have UA is 0. When UA is 0, you replace A here. So you're going to have U of C1 is going to be C1 A to the square root of lambda minus C1 A to the square root of lambda. And this is going to be 0. Right, so from the previous computation, I know that C2 is minus C1. I replace C2 by C1, so Ux is going to be C1 x to power square root of lambda minus C1 x to the power minus square root of lambda. Now, I'm gonna replace, I'm gonna consider the second boundary condition, right? UA is 0. So UA is 0, meaning that C1 A to power square root of lambda minus C1 A to power minus square root of lambda is 0. So then you have C1 A to the square root of lambda minus A to power minus square root of lambda is 0. So this C1 is 0, right? Because this term is different from 0. So C1 is 0. C1 is 0. So C2 is minus C1, and this is also 0. So you have U x will be 0. This is trivial solution. We don't take it. Right. So I explain again. This is an equation in which the coefficients are not constants. So in our class, we restrict our attention to two cases. If it is in a constant coefficient, you have exponential and then you have the characteristic equation. If it is not, you replace the polynomial into the equation, you get the characteristic equation, which is of this type, r squared plus lambda is 0. For this, you do exactly the same way that you do for the for the constant coefficient case. Case number 1, lambda is negative. When lambda is negative, then r squared is minus lambda, and this is the absolute value of lambda. So r1 will be the square root, the absolute value of lambda, and r2 will be the minus square root of absolute value of lambda. So u will be the linear combination with of x to the x to the power r1 and x to the power r2, right? So a remark is that in the previous case, if you have exponential, then it's just linear combination of the exponential, right? So you just have to replace exponential by polynomial. So basically, this is the form. You plug it back to the two boundary condition, and in this case, you find 0. This is a trivial solution, and we don't take trivial solution as an eigenfunction, right? Questions? Okay. Right, so now let us go to the second case. Case number 2. Lambda is 0. So let us try to do case 3. Case number 3. Lambda is positive, right? Case 2. Lambda is positive. You have r squared plus lambda is 0, which means that r squared is minus lambda, right? Which means that r1 is I square root of lambda, and r2 will be I minus I square root of lambda, right?
Wait, so why are we doing lambda equals 0 in this case too?
For lambda equals 0, I'm going to explain it in a minute. So for the case where lambda is positive, you have r squared is minus lambda, right? So which means that r1 is I square root of lambda and r2 is I square root of lambda. Now you have to plug this to the form. So you're going to have ux will be c1 x to the I square root of lambda plus c2 x to the minus square root of lambda. Right? So how do we continue? And what is x to the I square root of lambda? No, it's not sinus and cosinus. No. So let us go to this. This is C1, e to the log x, right? I square root of lambda plus C2 e to the log x minus I square root of lambda, right? Because x is e to the log x, right? And record. So when you have x is e to the n, right? So this power n is log of x. So what is log of x? Log of x is this power. So you write x as the exponential of n, and n is the power. So the log of x is this power, right? Which means that x is e to the log x. So here I'm gonna replace, yes?
So it's a cosine log x times root square of lambda plus I.
Excellent, yes. Can you sign the back of the paper, please? So now you have c1 e to the log x I square root of lambda, and c2 e to the log x minus I square root of lambda, right? To continue this, what we have is the following. So this I'm gonna write like c1 e to the log x times I square root of lambda plus c2 e to the log x minus I square root of lambda. Alright? So e to the log x to the power I square root of lambda will be e to the log x times I square root of lambda. And the other one is log x times minus I square root of lambda, right? So e to the A to the B will be EAB. This is what we use. Now I'm gonna pull I out to the outside. You have log x times square root of lambda plus c2 e to the power minus I log x times square root of lambda. Alright? So here you have cosinus and sinus, right? Because of the Euler formula. So e to the I will be cosinus of A plus I sinus of A. You're gonna use this Euler formula. e to the IA will be cosinus of A, I sinus of A. Right? So this I'm gonna have cosinus of log x square root lambda plus I sinus log of the square root of lambda plus C2 cosinus of log of square root lambda minus I sinus log square root lambda. Right? Questions? Now, in this case, I'm going to use this Euler formula. E to the IA will be cosinus of A plus I sinus of A. Right? So here I have I log of x times lambda and I minus I log of square root lambda. Again, e to the minus A will be cosinus of A minus I sinus of A. Right? So now I'm gonna have I'm gonna use the Euler formula. I have cosinus log of square root lambda plus I log of square root lambda cosinus log of square root lambda minus I sinus log of square root lambda. Right? So this gives me C1 cosinus log square root lambda plus I C2 sinus of log of square root lambda plus C2 cosinus log of square root lambda minus C2 I sinus of log of square root lambda. Right? So I expand everything. I have C1 cosinus I C2 C1 sorry sinus, and here I have C2 cosinus, and here I have minus C2 I sinus. Right? So this gives me C1 plus C2 cosinus square root lambda plus I C1 minus I C2 sinus square root lambda. Right? Yes?
Where do the x's go?
This one, so the x. Thank you. X. Another questions? You say at the back of the paper. Now I'm gonna put this with a big C1. Right? So I'm gonna put this with a big C1 and I'm gonna put this to the big C2. So I'm gonna have cosinus of log of square root lambda x and sinus of log of square root lambda x. No, I think x is inside. Sorry, this is a mistake. So this is square root lambda log x, right? And this is square root lambda log x. So this is square root lambda log x. This is square root lambda log x. Right, so this is square root of lambda log x. This is also square root lambda log x. This is square root lambda log x. Square root lambda log x. This is square root lambda log x. So here you have cosinus of square root lambda log x. Square root lambda log x. Right? So I'm gonna put this C1 plus C2 to be the big C1 and this IC1 minus IC2 to be the big C2, and I have cosinus square root lambda log x plus sinus square root lambda log x. Right? Questions? Now I explain again. This case is a little bit more complicated because you have I square root lambda and minus I square root lambda. Now you have ux is C1 x to the I square root lambda plus C2 x to the power minus I square root lambda, right? So you write x to be e to the log x, then you have e to the log x I square root lambda, e to the log x minus I square root lambda, Then you have e to the log x times I square root of lambda, log x minus I square root of lambda. Then you have e log of x square root of lambda, c2 minus e to the power minus I log of square root of lambda. Right? So then you split this using the Euler formula. You have cosinus square root of lambda log x, because e to the I log x square root of lambda will be cosinus square root of lambda log x plus I sinus square root of lambda log x. And the other one is giving you this one. You expand and you group them. You will see that here you have cosinus and cosinus. Here you have sinus and sinus. So they are C1 cosinus and C2 sinus. Right? Questions? So my question to you is, why in this case you have this complicated form and not in and in the constant coefficient case you don't have this? Who knows? If you can answer these questions, you can have 10 points to the homework.
Say it again.
The question is in this case, you have to deal with the Euler formula and everything to get this form. But in the case of the constant coefficient case, you don't have it, right? So you go directly to cosinus and sinus, right? So in the constant coefficient case, you have one. When you have this, you have R1 is I square root of lambda, R2 is minus I square root of lambda. You go directly to the case that Ux is C1 cosinus of square root of lambda x plus C2 sinus of square root of lambda x. So this is constant coefficient case. Yes?
So in the constant coefficient case, the form of Ux is already exponential, which is what we need in order to use the Euler equations. But in the variable coefficients,
Yes.
we're in
Can you sign the back and you said that you have 10 extra points. Yes, this is basically the case. Right. So in that case, this is what I have. They're the same mechanism, right? And just from here to here, you go through the same mechanism, because here you have C1 e to the I square root lambda x, right? Plus C2. Let me go slowly. So in that case, you have E1 x plus C2 e to the 2x, right? In the constant coefficient case, instead of polynomial, you have exponential. And then this is C1 e to the I square root of lambda plus C2 minus I square root of lambda x, right? And you use our Euler formula. You have cosinus of square root of lambda x plus I sinus of square root of lambda x plus C2 cosinus of square root of lambda x minus I sinus of square root of lambda x, right? And then you group them. You have C1 plus C2 cosinus of square root of lambda x plus C2 plus C1I minus IC2 sinus of square root of lambda x, right? So you put this to be big C1 and this to be big C2. So you have C1 cosinus of square root of lambda x plus C2 sinus of square root of lambda x, right? So in the constant coefficient case, you have this formula, and the reason behind that is because you use Euler formula, right? So you have C1 e to I1x, C2 e to I2x. I1 is I square root of lambda x, E2 is minus I square root of lambda x. So you use Euler formula, and you have C1 plus C2 cosinus square root of lambda, C1I minus IC2 sinus square root of lambda. You put this to be big C1, you put this to be big C2, and you get this formula over here, right? So in the two cases, yes?
So it's the only difference between the
constant coefficient normal, the ln x part?
Right.
Okay.
This is due to the fact that
Yeah, the other one starts off with d.
this is because of polynomial. Yes. Yes. This is the only difference. Right. Other questions? Yes.
So on an example, we can just skip down to the last part where we,
You go back. You go directly to this one.
so we go to UX, we don't have to go through all the ln.
Yes. So you go back. You go directly to this guy. In the exam.
For the test, we're gonna have to show it or just write it?
You go directly to this formula, and you don't have to go through all of the other formulas. Right? So now let us deal with this guy. Now we have to, so this is the formula that we got, and we have to solve the boundary value problem, right? Now you have u1 is 0. All right? Which means that you have c1 cosinus of square root lambda log 1 plus c2 sinus of square root lambda log 1 is 0. You have u1 is 0, which means that you can replace x by 1. So you replace x by 1, but log 1 is 1. Log 1 is 0. Which means that you have c1 cosinus of 0 plus c2 sinus of 0 is 0. This is 0. This is 1. So c1 is 0. All right? Now, so you replace and you get ux. This is ux. This is what we found. So you replace c1 to be 0, and ux will be c2 sinus of square root lambda log x. Right? Now you do this. You apply the same process. u1 is 0, which means that c1 cosinus of square root lambda log 1 plus c2 square root lambda log 1 is 0. Log 1 is 0. You find c1 is 0. Now you replace the second boundary condition. ua is 0, meaning that sinus of square root lambda log a 0, which means that square root lambda log a is n pi. So lambda will be n pi over log a square, and this is lambda n, right? And un will be sinus of square root of lambda n log x, and this is sinus of n pi over log a log x. Right? So I explain again. You have this general formula that you can use in the exam without proving it. Now you plug this formula into the boundary condition. The first boundary condition is u1 is 0, right? You have c1 cosinus square root lambda log 1 plus c2 square root lambda log 1. Log 1 is 0, so we have c1 cosinus of 0 plus c2 sinus of 0 is 0. So this is 0, this is 1, so c1 has to be 0. You replace 0 here, you're going to get c2 sinus of square root lambda log x. Now this is boundary condition number 1, and this is boundary condition number 2. ua is 0. ua is 0, meaning that sinus of square root lambda log a is 0, which means that lambda log a is n pi, so lambda n should be n pi over log a squared. Yes?
So like, we've only done 2 of the cases right now, like we haven't done the third case.
Yes.
But, so we just, every time whenever we plug the first boundary condition, we just assume that we can divide away the sine or cosine and have the...
No, here you have what? You have c1 is 0, right? So
Yeah.
you plug the first boundary condition, you have cosinus of 0. This is 1, this is 0. So this go away, so which means that c1 is 0.
Oh, the whole fact, yes.
Right? So this means that c1 times 1 plus c2 times 2 is 0. So this is c1 plus 0 is 0. So c1 is 0.
I see.
Yes. The next case is easy. It is also in the note. But you can see it in the note. But we're gonna go over it on Friday. But it's not difficult, right? So it's similar to the other case. So again, so let me briefly tell you what is going on in case number 3, right? So case number 3, lambda is 0, which means that you have x r squared is 0, right? So I is 0, right? So the solution will be a plus b of x, and you plug this into boundary condition. I'm gonna go over this one a little bit on Friday, but this is easy.